Hi everyone, my name is Anna Janicek, and today I will be talking about nanoindentation. Nanoindentation, which is also sometimes called instrumented indentation, stems from common macro hardness testing methods that were developed in the early 1900s like Brunel, Vickers, and Rockwell. These methods all determine hardness by taking the load applied onto the sample and relating it to the area of the indent left on the sample surface after the load is taken off. Starting in the 1930s, micro-hardness testing was developed, which used basically the same principles, but used lower indentation forces, which allowed for more specific placement location of the indents, and it also allowed more brittle materials to be hardness tested. In the 1970s and 80s, nanoindentation came about, and in 1983, the first system was released by Dr. Oliver and Sir John Pethica. And the benefit to nanoindentation was that you could gather hardness information about smaller features, including thin films and nanostructures. And then in 1992, a paper was released by Oliver and Farr, in which a majority of the theory behind nanoindentation is based off of today. It provides a mathematical formula for calculating the modulus and the hardness of a material based off of the load displacement curve that a nanoindenter produces off of a material. Finally, in the early 2000s, ISO 14577 was developed as the standard for instrumented indentation of metallic materials. So in nanoindentation, a continuously increasing load is applied onto the surface of a material until either a peak load or peak displacement into the sample is reached. And ISO 14577 defines the maximum depth into the sample to be considered nanoscale indentation to be less than 200 nanometers. However, it is still fairly common for most instrumentation and researchers to go beyond that and still consider it in the nano range. Most indenter tips are made of very hard materials in order to resist the wear that comes about from continuously contacting materials. So these tips are usually made of hard tool steels, tungsten, sapphire, or most commonly diamonds. The probe tip can come in many different shapes and sizes. The Berkovich tip, which is a three-sided pyramid, as seen here, is the most common because it can keep a really sharp tip easily and be manufactured easily, and it can also cause plastic deformation at low indentation depths, making it an ideal choice for thin film analysis. Another common indenter shape is the spherical indenter, and this shape is most often used for highly elastic materials or for understanding the elastic to plastic transition within materials. And then similar to atomic force microscopy, it's extremely important that the tip be as close to geometrically perfect as possible so that the contact area is correctly calculated. So like I said before, the most well-known theory was developed by Oliver and Farr, and the main principles behind this are that when you load most engineering materials, there's an elastic and a plastic response to the material, and then when you unload the material, the elastic portion of the response recovers, and the plastic portion remains behind as the shape of the indent on the sample. So you can see that here with the elastic and plastic being the loaded, and then the plastic being this unloaded curve here. And nanoindentation outputs results as a load displacement curve, and Oliver and Farr were able to take the values of the unloading curve and from these calculate formulas for both the hardness and the modulus of a material. So for the hardness, this is a relatively simple formula where you take the maximum load applied on the material and divide it by the contact area. And so here's where it's super key to have a proper contact area calculation for the tip. For modulus, it's a little more complex. So a maximum stiffness is derived from the slope of the tangent line of the unloading curve at the maximum depth of the sample. And from this stiffness, using the contact area and then a geometrical correction factor for the tip beta, you can get a value for the reduced modulus of the system. And then using the reduced modulus value, the modulus and Poisson's ratio of the indenter tip, and then also the Poisson's ratio of the sample, you can get a value for the modulus of your sample. So nanoindentation is able to provide a lot of mechanical property information, including for thin films, highly elastic materials, bulk materials, as well as brittle materials or coatings. In some operation modes, nanoindentation can also provide information as a function of depth. giving information up to about 1 micron. So one of the key things is that you can get hardness and modulus values in standard units instead of hardness scales that are typically seen in macro hardness testing techniques. You can get information about the elastic to plastic transition, creep by applying a fixed load over a period of time and getting the depth versus time curve, as well as fracture toughness. In a lot of load depth curves, you see these break-in points, and these could be caused by cracks in the material in which you can extract the fracture toughness information from. Unlike a lot of other materials characterization techniques that we've learned this semester, we are not able to get elemental composition, microstructure, or chemical state information from nanoindentation directly. So in terms of instrumentation, most nanoindenters are set up very similarly, although there's a lot of extra features that can still be added based on what sort of experiments you're trying to run. So most nanoindenters have a load coil or magnet, which controls the load force being applied to the sample, the indenter tip, a displacement sensor, which measures the z direction, how far the probe is for the displacement going up and down, sample table for an XYZ movement of the sample to place under the indenter, and then computer software to visualize the load displacement curve and then calculate the modulus and hardness values. There are some optional instrument components that are pretty commonly seen. Optical microscopy lenses is the first to help see approximately where you will be placing an indent on your sample. After indentation, though, you do need to use SEM to see the sample because of the size of the indent is less than what optical microscopy can resolve. Furthermore, you can get heating, sample table, and indenter heaters to perform high temperature nanoindentation testing, anti-vibration stabilizers. Nanoindentation is extremely sensitive to vibrations, and so having these will help reduce some of the measurement errors. And then it can also be coupled with atomic force microscopy to get information about surface morphology or microstructure. And then if you're high temperature testing, it is preferred to do it in a vacuum or an inert gas environment to help prevent the tip and the sample from oxidizing. So there's two main operation modes that nanoindentation operates in. The first is the depth sensing measurement, and this is your standard nanoindentation measurement where you apply a load to a maximum load or displacement, then unload the curve, and then you get a hardness and modulus value calculated from it. The second, and perhaps this one is used more commonly, is the continuous stiffness mode. And in this mode, you apply an oscillating force to the sample at a set frequency, and you basically get these smaller loading, unloading curves within your load displacement curve. And this allows you to calculate hardness and modulus throughout the entire depth of your indentation, which could be particularly useful for thin films for understanding what the potential substrate effects are as you indent deeper into your film. And then lastly, high temperature nanoindentation, which can be completed in either of these two previous modes, but you can measure the hardness and modulus of your sample up to about 800 degrees Celsius, and you heat both your indenter and your sample at the same time to ensure uniformity in the temperature of the test. Downside to this is there's usually a thermal drift factor that you introduce due to the just general differences between the tip temperature, sample temperature, and the ambient environment. And so to correct this or minimize this, it is recommended to try and stabilize your sample and your tip for as long as you can in order to sort of get thermal equilibrium before performing your measurement. So in terms of accessibility of nanoindenters, the equipment can range from small tabletop indenters to enclosed standalone equipment. The larger instruments with more enclosed systems are often equipped with better load and displacement sensors and are better acclimated to accounting for thermal drift and minimizing external vibrations. And then similar to atomic force microscopy, the equipment can cost anywhere from about $50,000 to a few $100,000, depending on the features that the equipment is equipped with. It is common for research universities to have nanoindenters, as well as corporate research labs may have nanoindenters that are more tailored to like production scale indentation instead of specific high temperature testing or things like that. And then lastly, one of the expenses to consider is the probe tips. They can range anywhere from about $1,000 to $5,000 depending on the material and the accuracy that you need to get out of them. So as previously stated, it's pretty common to use nanoindentation to study thin films and brittle coatings. And so this is an example of that from a study published in May 2024, where they used titanium gold intermetallics as a wear-resistant thin film that could be applied to titanium implants, typically used for knee or shoulder joints. And so in this study, the titanium-3 gold intermetallics were applied onto both gas and titanium-6,4 substrates using a physical vapor deposition process, both at room temperature and at 275 degrees C, and then the hardness and modulus values were measured. And what was seen was that from the load displacement curves, on glass, the room temperature samples performed about the same, and then on the titanium-6 substrates, the room temperature samples performed differently. And this was sort of resultant of the overall surface roughness of the titanium-6,4 samples. Nanoindentation is an extremely localized measurement, so having small differences in surface roughness can cause differences in your hardness values. And that was sort of seen here in your hardness graph as well. So in the samples deposited at 275 degrees Celsius did show a higher hardness than the samples deposited at room temperature. And again, on the titanium substrate, there's larger error bars, which is reflection of these discrepancies here. In terms of modulus, the samples were a little less clear, although the modulus on the titanium substrates was deemed to be lower. And this is what researchers deemed to be because of the modulus being more substrate sensitive than hardness. Another common issue with nanoindentation of soft or elastic materials is the inability of the indenter to realize that it has already penetrated the surface of the sample. And so work completed by the National Center of Advanced Tribology in Southampton aimed to determine how low of a hardness or modulus nanoindentation can detect and whether or not it can maintain resolution at these low loads. So polyethylene glycol hydrogels were formed with different compositions and varying levels of cross-linking agents to determine what the differences in mechanical properties could be detected. And typically, instruments that they had would only start to detect a load versus displacement curve after a load of about 10 micronewtons is detected. And for some of the hydrogels, this may not happen until tens of microns into the samples, which can be seen here. And so to correct for this, researchers put their own 0 point on the sample when they knew the tip was interacting with the substrate in order to get more accurate results. And from this, they were able to see a very clear increase in modulus with cross-linking degrees in the kilopascal range, and then also was able to data match the nanoindentation results to results from AFM, microindentation, as well as overall compressive macro scale hardness testing. And then they were able to verify the accuracy of their results using cantilever beams that were made to mimic the flexural stiffness of the hydrogels that were indented, and the resultant load versus displacement curves were pretty comparable to the hydrogels, as you can see here. So for the sample requirements, ideal measurements are based off of flat samples that have been polished to a pretty fine level. Overall indentation is pretty non-destructive itself. The indents can be polished out if they're needed, but a majority of the destructive nature of the test is dependent on the degree of metallography required to just prep the samples. Reference samples are required to make sure that the tip is in good condition and the sample is calibrated. Typically, a fused silica or quartz sample is used in order to calibrate the equipment. And this is also important for making sure to minimize or correct for thermal drift or vibrational drifts. In terms of resolution, it does depend on the instrument, but typical displacement resolution is usually less than 0.01 nanometers and could go down to picometers. And the load resolution is around 50 nanonewtons. And this resolution is an extreme benefit compared to some of the larger scale macroscopic testing resolutions. The maximum load is again dependent on the equipment, but can range anywhere from 10 to 50 micronewtons millinewtons, and the penetration depths can range anywhere from 1 nanometer to 1 micrometer, but most equipment can accommodate going deeper depths. It is important, again, to note that this is an extremely local measurement and may not be able to provide information about the modulus and the hardness of the sample as a whole compared to a lot of the macroscopic testing techniques. And then compared to other techniques, nanoindentation is more expensive. It does require that the SEM is used to image the indents if needed. However, it can be coupled with AFM, and it is able to provide measurements in standard units for comparison across experiments. And then also similar to other hardness measurement techniques, you can't image and indent at the same time, and so that is one of the downsides of indentation overall. So overall, nanoindentation is a easy and relatively non-destructive method of obtaining mechanical property data of materials and their small scale features. And a lot of the advantages include that you can have high temperature testing, you can indent thin films, brittle materials, and highly elastic materials. You can get information over the course of depth. You can couple with AFM, and there is extremely high resolution in the measurements. Some of the disadvantages do include that it's more expensive than typical hardness testing. The machine and tip do need to be calibrated very closely for accurate measurement results. Thermal drift and vibrations could cause a lot of uncertainty in the measurements. And then you could get this phenomenon called pile-up or sink-in. This is when the load induced in the material causes the material to either pile up around the indenter or sink in around the indenter, which causes incorrect calculations on your contact area. And pile-up is typically seen in low work hardening materials, while sink-in is most common in high work hardening materials. And then finally, it could be difficult to detect the surface of highly elastic materials, but more research is being done on trying to correct for that.